Right. And then there's also, I'm
Patrick, you've got your hand up. Is that just from a remnant from my asking if you're going to survive the next 4 weeks, or did?
Yes, sorry about
Yeah.
that.
Okay. Hey, no problem. All right. I was sharing my tablet. All right. 10 November. Province stats. Okay. So just some notes. Last time, um, I shared with you some screencasts on point estimates and point estimators, right? And I pronounce it funny just to remind myself to make a distinction, a vocal, verbal, audible distinction between estimates and estimators. Um, Point estimates, right? These are numbers. Point estimators, these are random variables, right? So estimates come from estimators. The screencast, there's a 3-part screencast. It talked about what these are, how you make them, what issues are surrounding estimators. How can you tell if you have an estimator that is good? Talk about the goodness of an estimator. And then part 3 talked about a likelihood. If you know kind of how you want to build an estimator, how can you build the best one given a little bit of data? So if you haven't watched those yet, make sure you go watch them, or you can just read from the text. I really hew pretty closely to the text. Yeah. I will say that the estimators that are most important to us are the sample mean, the sample variance, and there's this thing called the sample proportion. And then this hat notation is notation that the book uses, and it's very standard in statistics, that if you have a statistic, or rather, if you have a parameter that describes some aspect of your population, denote that parameter by a theta, then the estimator associated to that parameter, you just take your parameter notation and you put a hat on it. The 2 exceptions are the sample mean and the sample variance. Those are so common that they've aged into their own notation, so they don't have to follow the hat notation. All right, so review that stuff. Today, I'm going to talk about something that's called the central limit theorem that gives us some information about the sample mean that's really pretty cool and really important. And it's called the central limit theorem because it's central to the theory of statistics. It's super important. It's central to the theory of statistics. It's used a lot. So I'll tell you what that theorem is, and we'll work a couple examples to show how we use it. The next time, we're going to begin the end of the course. Now, yes, the 4 weeks left dictates the end of our course, the clock, the calendar. But we're going to start the topics that'll just cap off the course. I've been telling you that we've been going to do this. It's the topic of inferential statistics. And this comes at us through chapter 5 and chapter 6 in the, what's the author's, Navidi? Yeah, Navidi text. Chapter 5 is on confidence intervals. And chapter 6 is on hypothesis testing. So I'll give a quick intro to confidence intervals at the end of class today. But those, I think those chapter 5, talking about a sample of information from chapter 5 and a sample of information from chapter 6, that'll round out the semester. And I'll give you another set of practice problems to work on too that reflect point estimates and confidence and the central limit theorem that I'm going to talk about today. Okay, so before I start talking about the central limit theorem, does anybody have any questions they want to ask about material we've talked about so far? I'm not hearing anything.
So the book was saying that we could get a lower mean squared error than S if we want to estimate the population standard deviation.
Okay, yeah.
So why do we use S?
So let me make sure I understand your question. So there are 2 ways that we could measure, let's call it the variance, the sample variance, since the standard deviation is just the square root of the variance. So our definition of the sample variance is 1 over n minus 1, where n is the sample size of the square of these errors, or the square of the deviations of our values from the mean of the sample mean. Right. So this is our standard point estimator for the variance of a random variable, the variance of a population. So as I understand your question, Patrick, what you're saying is, well, if we could define the sample variance in this way, right? And a rational, normal person, an educated person, would think this is the way you want to define the point estimator for variance, right? It's the mean of the deviations, squared deviations, right? Doesn't that make sense? Is that kind of what you're asking, Patrick?
I don't remember if that was the formula they gave, but I remember that they said that the second one would have a lower mean squared error.
Yes. Okay. So the textbook works out this example that if you calculate the mean squared errors for both of these estimators, okay, and the mean squared errors are the standard measure of goodness for an estimator. And goodness, yes, it's a real word in statistics, right? And it is a principle that if you have two estimators for a given parameter, the better one is the one that has a better goodness score, a lower mean squared error. Well, turns out, read the text. The variance hat has a lower mean squared error term than the sample variance definition that we've been given. So an educated argument can be made for this being the preferred definition. So the question is why? Right? So why this one? Or why not this one? Why this one? That's what I hear your question is, Patrick. Is that right? Kind of?
Yes.
All right. Anybody want to take a stab at why textbooks and statisticians stubbornly maintain that the first one is the definition we should use for the estimator?
So the advantage the book cited was that S squared is unbiased, but it's not clear to me why we're not applying that uniformly to all of our estimators.
So I'm trying to think about how to answer your question, and so I'm going to start talking before I figure it out. You mentioned, answer to my question, the reason that the estimator with a larger mean squared error is used is because it is unbiased. It's the unbiased estimator. It has a slightly larger mean squared error than this other estimator, but the other estimator is biased. That is to say, its mean is skewed away from the population mean. The mean of this estimator is skewed away from the mean of the parameter it's trying to estimate. Whereas this statistic, its mean is exactly equal to the mean of the variances. So that means that this is a more accurate estimator than this. I'm using accurate in the technical statistical sense, where when we talk about error, we talk about the precision and accuracy. Precision is where your standard deviation is small. Accuracy is how close you are to the actual parameter, right? on average. The sample variance is more accurate. The standard, this estimator is inaccurate, and that's why we prefer this one. There may be some cases where you prefer to use something that has a smaller mean squared error, and you can, if the situation warrants it, you could use this definition. But when all of the things are taken equal, we prefer something that's unbiased. Okay, so your second comment, Patrick, was something about how the book seems to unevenly apply this criterion of bias. Is that right? Could you?
Yeah, I mean, the estimator that they suggest for a lot of things is the maximum likelihood estimator. And I don't think that's always an unbiased estimator.
Yeah. Yeah. So what's happening there, let me see if I can piece this out for you. So we have the topic of estimators. Okay. And if you have a definition of some estimator for a parameter theta, then say if you've got definitions, then you can compare using their mean squared error. So you can compute the mean squared error of one estimator with another mean squared, or with the mean squared error of another estimator. So you can make a comparison between the two to decide which one's better. Okay, so that's one approach, or one thing the textbook has been talking about. If you don't have a definition and you seek a definition, the textbook says you can use a maximum likelihood approach. So if you know something about the distribution of, or the way the data is distributed, then you can use a maximum likelihood approach to use that distribution to find a value. Like the example that the book uses is a binomial NP. And you know your sample size, but the MLE shows you how to pick the proportion.
Oh, I see. So we're just doing that because there isn't a super nice, convenient way to find a unbiased estimator in that case.
Right. That's right. That's right. So it's kind of a different situation. Is that helpful?
Yes.
Okay. And that conversation about the maximum likelihood stuff, I mean, it's cool because it uses calculus and it uses logarithms. Right? And so you can kind of get your geek on by doing those things. And the logarithm, I think it's really beautiful how it simplifies the function that you're looking for a maximum of. I mean, it's really kind of beautiful. So, of course, a student in pre-calculus who is hating logarithms when you're trying to teach them about logarithms, this maximum likelihood estimators aren't going to be a good example to pull out for them. But anyway, nonetheless, it's cool for us. Right? Does that answer your question, Patrick?
Yeah, that was a really thorough answer.
That was a really what?
Thorough answer.
Oh, well, yeah. Any other questions? Anybody else have any other questions? Okay. So let's talk about the central limit theorem. So this is chapter 4, section 11. There's a couple other good sections in chapter 4 that I am tempted to talk about, but I'm just gonna pass them by. We'll go back and pick them up if we need to. One of them is a section on probability plots. So if you're ever having problems falling asleep some night and you want to put yourself to sleep with an interesting topic, read that section on probability plots. But I digress. The central limit theorem. So the central limit theorem is going to tell us one of the reasons that the normal distribution has primacy in the theory of statistics. The normal distribution, the bell-shaped curve. So at its mode, at its highest point, that's the mean, and at the inflection points, that's where the standard deviations occur. Super important probability distribution for us. But the way we start talking about the central limit theorem is that we don't care what distribution we're talking about. So we're going to let x be a random variable. And we don't care what kind of distribution it has. It could have any sort of distribution. It could be binomial, it could be Bernoulli, it could be exponential, it could be Poisson. It could be normal as well. We just don't care. So we've been talking about sample statistics, point estimators, and the most important one to us is the mean, the sample mean. And so the central limit theorem will talk about the sample mean. So we're going to let x bar be the sample mean for x, where we take a sample of size n. I could put a subscript on that x bar, but little n is going to be our sample size. So if the original random variable x has mean mu and standard deviation, well, yeah, sigma, then we've studied that x bar has mean mu as well, and it has variance. We'll call it, yeah, maybe I should write that this way. Let's just be consistent. The mu of x bar, the mean of x bar is the mean of x, and the variance of x bar is the variance of x divided by n. So these are just facts about the point estimator for the sample mean. It doesn't tell us anything about how this new random variable is distributed. It just tells us what's the central tendency of this new random variable and what's the tendency of the spread, or what's the tendency of the error. Right? It's there. And you'll notice that if I want less error in my estimates, I can just make my sample size bigger, right? And that will decrease the variance of the sample mean. So here's what the central limit theorem tells us. So I'm going to start out setting up the hypotheses for the central limit theorem, and it's basically just formalizes what we just talked about here. So let the random variable x sub I, which is just going to be a copy of a random variable x, represent a sample from x. And here I goes from 1 to n. So we've got a sample of size n. Let x have mean mu. And variance sigma squared. And we'll define the sample mean random variable as the in the standard way. Right, it's going to be the average of the n other samples. Now I'm going to let S sub n be n times the sample mean. So just, oops. So we're clear what that means. It's just the sum. It's the sum of the other random variables. That's why I'm using n. Then the central limit theorem tells us if n is sufficiently large, then the sample mean is going to be distributed like a normal random variable with mean mu and variance sigma squared over n. And the sum of the observations is going to be distributed like a normal random variable with mean n times mu and variation or variance n times sigma squared. That's the central limit theorem. So a couple comments that I want to make about the central limit theorem, and then we'll do some examples. So the first comment that I want to make is this part is not new. We have already seen that if you start with a random variable and you calculate the sample mean from that random variable, the sample mean will have mean mu and will have variance sigma squared over n. That's not new. What's new is the fact that the sample mean as a random variable will follow the normal distribution. That is, it'll have this shape. No matter how wacky the probability mass function for x is, the mean follows this shape, and that's remarkable. This result really follows from the work that we've already done about combinations of random variables, so I don't need to say anything here. Just emphasize that the fact that the sample mean is distributed as a normal random variable is deep, and that's what the central limit theorem tells us. The second comment that I'll make is this, has to do with this right here, and I'm gonna, yeah. If n is sufficiently large, so if you're like me, or like the me that I like to think myself as, who's a kind of a, what's the word, curmudgeon, you know, pessimistically optimistic about things. You see this and you say, well, what the hell? Insufficiently large, what does that mean? And so I'm about to tell you what that means. Note, it is commonly accepted that n, a sample size of 30, is universally sufficient when you apply the central limit theorem. Okay. N equals 30. So I'm going to go back to the theorem statement. I think I might have forgotten something. I did forget a word. I think this is important. So the sample mean is not distributed exactly as a normal distribution, but it's approximately as a normal distribution. So when we substitute a normal distribution for the distribution of the sample mean, we know we're not being we know it's not being perfect, but it's close enough where it's habitually done. Right? It's a standard practice to make that swap. Okay, but I think it's important, and this is why I went back and wrote it down, that the, the distribution is approximately normal. And the bigger n gets, the more closely the distribution of the sample mean becomes normal. Okay? But there's always a little bit of wiggle room. That's largely overlooked. Okay. Any questions about this so far? I'll do an example here in a second. But I want to make another comment. And as I was preparing for the lecture today, I realized something. And this is going to be a mistake that I'm going to tend to make. And now that I know that it's there, I'll be less likely to make it. So the textbook when it uses the notation, for the normal distribution, it has two parameters. It's got the mean and it's got the variance. Okay? This is how the textbook lists these things. So when you see the textbook write N3, 0.5, you got to look at this number and remember it's the variance. Okay. So Dr. Miller, why are you bringing this up? R does it differently. When R uses like the probability distribution for the normal distribution, where the book puts variance, R puts the standard deviation. So just remember that. Don't get tripped up. Don't get tripped up by going back and forth between the book notation and using R. You'll accidentally use the variance. You'll accidentally use the variance instead of the standard deviation, and that will change your numbers. That will change your answers. Okay, let's do an example of applying or using the central limit theorem. So one of the things that I like to do as a professional mathematician is I like to study bats. And bats are hard to study because they fly, right? They're the only flying mammal. And they fly at night when you can't see them. And when they're flying around at night, they're generally eating. That's why they fly around. They're eating insects. In North America, our bats primarily eat insects. Or in the United States, our bats are insectivorous. But when they're flying around and eating, they're looking for their prey by making noises that humans can't hear. So bats are really hard for people to study. So when I study them, I put out a recorder at night that has a microphone that records in the ultrasonic range of sound. And then I get up in the morning and I look at the SD card to see if my recorder recorded anything. So this example is going to talk about that. So when I get up in the morning, I take my SD card out of my recorder. The number of bats that appear in a single recording varies. Yeah, recording is short. And imagine I've made thousands and thousands and thousands and thousands of recordings, and imagine that I've kept a tally of how many bats have appeared in each recording. And the probability mass function or distribution, the number of bats that appear in the recording is given by the following table. So if X is the number of bats, you have maybe up to 4 bats in a recording. And the probability that X bats appear in the recording are 31% for no bats, 51% for 1 bat, 15% for 2 bats, 2% for 3 bats, and 1% for 4 bats. So suppose I wake up in the morning and there's 31 recordings waiting for me. What's the probability that the average number of bats that I recorded is 1 or more? So looking through all the files, what's the probability that I've recorded, have 31 recordings with bats in them, or 31 bats recorded across all my recordings? All right, so this is we can apply the central limit theorem to this because I have more than 30 recordings and I'm asking a question about an average, a mean. So if X is the number of bats in a recording, I can define X bar, the sample mean, as the average number bats in 31 recordings. Okay. So how do I figure out what's the probability that the average number of bats that I've recorded is bigger than or equal to 1? All right, let's use the central limit theorem. Well, the central limit theorem says that, well, first of all, to use the central limit theorem, which tells us something about the distribution of the sample mean, I need to understand the distribution of my original random variable. So I need to understand what's the mean and the variance for X. So the mean, I mean, this goes back a ways. What you do is you add up the probability of X occurring, and then you multiply it by X. And if you do that for this data, I think you get 0.91. So on average, each call recording has 0.91 bats in it, which is an impossibility, but this is just an average. The variance is something similar, right? The variance is the sum of the probability times, let's do this right. Probability times the deviation squared. And if you do that for this data, you get about 0.62, I think. Yeah, 0.62. So let's look back at the central limit theorem. The central limit theorem tells us that the sample mean will be distributed as a normal random variable with the same mean as my original random variable. And the variance is going to be this, the variance of X divided by the sample size. All right, so let's, we need to go on to the new page. So the mean of my sample mean is going to be my original mean, which is 0.91. And the variance of my sample mean is going to be my original variance divided by the sample size, which is roughly 0.03. Okay, so this tells me the sample mean is going to be distributed like a normal random variable with mean 0.91 and variance 0.03. Okay, this is using the book's notation. Let me think here for a second. Actually, it's a little smaller. Okay, so we want to figure out what's the probability that this mean is bigger than or equal to 1. Okay. So either your mean could be bigger than 1 or it can be smaller than 1. So the way our probability mass functions or our cumulative distribution functions work is they work by calculating, too many bars. They work by calculating when a probability is less than or equal to a value. Oh, yeah, that's right. So in R, that means that this is the command pnorm, and then we put in the number 1 because that's this number. And then we put in mu, and then we put in the standard deviation. So if we throw that into R, we'll get this, 0.0013, right? So that's a very small chance that the average number of recordings of bats in my files is going to be bigger than or equal to 1. Right? And it's exactly 0.13% chance. Right? So that's how we use the central limit theorem. Although I know something about the distribution of the counts of my bats in my recordings, I don't use that when I'm asking a question about the sample mean. Because my sample size is big enough, I can use the central limit theorem. And then I can use a built-in function in R to do my calculation. If I want, for some reason, to use this original distribution, I could do it. It would take a lot of time because I'd have to look at this distribution, and then I'd have to figure out how to build a distribution for X bar. It's much better, much easier to use the central limit theorem so I can use the normal distribution. All right, so that's an example of how we use the central limit theorem. One thing that the book will talk about that I want to say something to you about, it may be obsolete. We may not have to worry about it at all as a group, the 20 so of us, as we talk about this stuff this semester. But the book is going to talk about it, and so I want to make sure you understand what the heck the book is talking about. And this is the idea of a z-score. So I'll just stay on this page. I've mentioned Z before in this class. So I'm going to remind you what Z is reserved for a very special random variable in statistics. And this is the random variable to which z-scores refer. If I were to write a random variable is distributed like a normal random variable with mean, mu, and variance sigma squared, I write this. The z random variable is the random variable that's the normal random variable with mean 0 and standard deviation 1. Okay. So this is Not standard deviation. Well, it doesn't matter. Variance 1, then the standard deviation is also 1. So z-score. So let me tell you what a z-score is, and then I will come back to these random variable distributions. Suppose X is distributed normally with a mean mu and variance sigma squared. As so often happens. There is reason, or historically has been reason to want to transform this data. So if little x is some element of the sample space of a random variable x, and I'm just going to abuse notation and say this, then we can, if you look at the points, let's say x minus mu, so take all the outputs and subtract mu. This set has mean 0 by linearity of the mean. Okay. So I could take my random variable and I could subtract a constant from it, and I'd get a new random variable that has mean 0. Everybody with me? Yep. All right, so I could also take one of those shifted numbers, and I could take that difference and I could divide by the standard deviation. Then the set of numbers here, which are coming from this random variable, this set has variance equal to 1 over sigma squared, right? That's this constant multiple. 1 over sigma squared times the variance of x minus mu, and shifting doesn't change your variance. So this set has variance 1. So these two transformations that I just did, where that my set of x's go to the set of x minus mu over sigma, they've transformed a set of data that had mean mu and variance sigma squared to a set of data that has mean 0 and standard deviation 1. And this is that very special normal distribution that's denoted by a z. And so if you take a number x and you transform it to x minus mu over sigma, this is called the z-score of x. So whenever the book talks about a z-score, this is what it's doing. It's taking your normally distributed values and transforming them so they're now coming from this other distribution. So what's happening here is that if you've got a normal distribution x, it's a little messy, x with mean mu and standard deviation sigma, and you transform it to the normal distribution, and it's going to have mean 0 and standard deviation 1. What happens is that if you've got some x naught that's distributed from x, it gets transformed to a z naught. So let's write that z naught equals x naught minus mu over sigma. What happens is that the area here, which is the probability x is less than or equal to x naught, That's the same as the area down here, the probability that z is less than or equal to z naught. So historically, what's happened is that it's hard to compute these probabilities with normal distributions because of the integration problem that they present. So statisticians came up with lots of great tables for values of areas like this. So it was easy for people to calculate these things. And with the idea of a z-score, they could take any normal random variable, translate it into this situation, and then use these tables. Historically, that's why z-scores are important. This idea of z-score also kind of emphasizes the value and the role that normalizing data can play. When I'm on a committee, we got a bunch of people like evaluating applications for the SURF program in the summer. And every faculty member that's evaluating might score things differently. But what I can do is I can take the different scores people make and translate them into z-scores according to their mean and their standard deviation. And then suddenly their scores are always comparable to everybody else's scores, because you're using their internal bias and their internal spread to, you're kind of getting rid of it. So this idea of z-score is a useful one even outside of our class. So you see z-scores, this is what's going on. This is what's going on. Now, why might this be irrelevant to us in this class? It's R. R can calculate the crap out of this stuff. R doesn't have to take your random variable, translate it into the standard normal, and then calculate this, and then come back and tell you what that is. R does this right out of the box. So thank goodness for, ooh. Oh no, wrong. This here, let me do this right. This command in R gives us this value, all right? And we don't, so we don't have to mess around with all these transformations. So even though we don't need to mess around with these transformations, I'll just repeat. The book doesn't know that we're using R. The book thinks that you're taking stats 5 years ago when everybody had to use these tables. So when it talks about z-scores, I don't quite know if you can kind of skim over that and not pay attention, because there is value in this process of using z-scores. But if it ever tells you to calculate this probability by going to a normal distribution, that you can say, don't worry, I've got R, okay? So exercise a little judgment. And if you have any questions about that, if you're ever confused about that, don't hesitate to ask. Okay, so the book has another section on the central limit theorem and binomial distributions. So it's worth talking about these for a minute because the ideas will come up again later. So imagine we're in the case where we've got a random variable that's distributed as a binomial with parameters n and p. Remember, the central limit theorem doesn't care how your random variable is distributed. It tells you that if you go and you calculate the sample mean, your sample mean is going to be distributed as a normal random variable. Here we're going to say, well, suppose we know x is a binomial. The binomials are important for us because they're the classic situation where we might want to have an estimator for this p. And this is a proportion. when we learned about binomials, we learned about them in the context of a Bernoulli random trial. And the parameter for a Bernoulli random trial was P, the probability of success. But we also now are interpreting that P as a proportion of successes. Our favored estimator for proportion is X over N. That's the maximum likelihood estimator for proportion. Well, I'll come back to that. So a binomial model is a repetition of N Bernoulli trials. So if I say Yi is a Bernoulli trial with probability P, so X is a repetition of N of those trials, then we can conclude that my estimator here is really just a mean of this. It's the maximum likelihood estimator of the sample mean of the Bernoulli trials. Okay. Oh, I missed the word mean. So because it's a sample mean, that means we can apply the central limit theorem to this estimator for proportion. So that's kind of cool. So now we're taking the central limit theorem and extending its application realm. Not just the sample mean, but now we're applying to the sample proportion. So here's the standard way, or here's the consequences. Recall that a binomial random variable with parameters N and P, it has a mean of P. No, let's see, a mean. That's not right. The mean of this thing. Oh, here. It's the Bernoulli. The Bernoulli random variable. Okay, since P hat is the maximum likely estimator of the sample mean of Bernoulli trials, it's the Bernoulli random variable we want to know about. So the mean of the Bernoulli trial is P, and the variance of the Bernoulli trial is P times 1 minus P. Right, easy computations, we did them a long time ago. So the central limit theorem says that this P hat, which is the sample mean estimator for the Bernoulli trials, is distributed as the norm. Oh, let's see here. Now, let me back up a second. X is the sum of these things. And so the central limit theorem said that this was an SN. Okay. So the sample mean of these Y's is 1 over SN. Okay. That's 1 over X. And that's X over N, right? That's P hat. That's what we're talking about. So what does the central limit theorem tell us about the distribution for P hat, which is Y bar? And let's go back and look at this central limit theorem. So here's our central limit theorem. Our X's here are our Bernoulli trials. We add up all these Bernoulli trials. So let's see, we were calling that X. So we can say our the central limit theorem says our X is distributed this way. So we have n times the mean and n times the variance. So let's do that. Let's copy that down. So Sn is distributed normally by n times the mean and n times the variance. So our mean is P. Our variance is P times 1 minus P. All right. And so P hat is 1 over n times Sn. And using what we know about linear combinations of random variables, if you divide the mean by a constant, that divides, if you divide a random variable by a constant, that divides the mean by that constant. And the same thing happens with the variance. Oh, you divide by the square. So we divide the variance by n squared. That cancels with one n in the top. So this is the upshot. By the central limit theorem, I'm going to circle that in color. By the central limit theorem, the sample proportion as an estimator is distributed as a normal random variable with these parameters. And if I have time, I'll work an example of that. Let's copy this over to the next page. Oh, come on. Before I do an example, let's make a note. It's commonly accepted that this approximation works when, okay, I haven't finished my sentence yet. Remember, the central limit theorem says when n is sufficiently big, the sample mean is approximately equal to a normal distribution. It is approximately distributed according to a normal distribution. Then we ask the question, well, what does big mean? And I told you that it's commonly accepted that n equals 30 is big enough. So here for the population proportion, that number changes slightly. It's accepted that if n times p is bigger than 5 and n times 1 minus p is also bigger than 5, then that's big enough. Then you can use the central limit theorem for population proportion. But 5 is kind of small. It's preferred that these numbers are both bigger than 10. So if both of those numbers are bigger than 10, you're golden. If you're between 5 and 10, I think you just need to be careful. You do it and see what happens. Okay? But it's accepted that 5 is sufficient. Anything smaller than 5, you should say you can't apply the central limit theorem to your estimator for proportion. But if everything's bigger than 10, if both of those things are bigger than 10, you're really good to go. All right, so let's do an example and we'll call it a day. Well,
Professor, how are we supposed to figure that out if we don't know?
If you don't know P?
Yeah, we're looking for what we're looking. We want an estimate. We want an estimate for P, but in order to check to see if it works, we need to see if NP is greater than or equal to 5. Sorry, it's greater than 5.
Yes, this is one of the classic questions in statistics and estimators. Even if you look in the red box, right? I got p hat here, but I've also got p on the other side. Yeah, so how do you do that? That's a good question. A question I had not thought about.
Does the rule also work if I say NP hat instead of NP?
Again, that's one of these great classic circular questions in estimators that I'm sure there's an answer out there for it, but I need to go look. So let me write this question down just to memorialize it, as they say, and then I'll see if I can find an answer. Okay, that's a great question. That's a very good question. And it might be obvious and I'm not thinking clearly, or it might be not obvious, but I trust that it's not obvious. So let me go check on that and see if I can come up with an answer. So let's turn to another bat example. So my bat detectors record throughout the night, and suppose in the morning, my bat detector has 2,000 recordings. For me to look through, okay? I can't read them all. But if I say X is the, let's see, it's going to be the random variable that tells me whether or not a bat was recorded in a file. So it's going to be a Bernoulli random variable, not a Bernoulli. Yeah, a Bernoulli. Was a bat recorded? So if I let that be my random variable and I look back at that other table I showed you before with that probability distribution function, I can say that the probability distribution of this random variable is this. There was a 31% chance that there's no bat recorded in a file, and there's a 69% chance that there was a bat recorded in a file. So if I can review, suppose I can review 40 files. That's how much time I have. If I take 40 files, then I've got a sample size of size 40, which is bigger than 30. And so I can use the central limit theorem to, it'll allow me to use the normal approximation for the number of bats, or the number of files out of 40 that contain a bat, a recording of a bat. So notice this is like a binomial distribution, sample size 40 with probability 69. Okay, and I'm going to use the normal approximation for that. So what's the probability that I have at least 32 files that have bats in them? So what is the probability I have 32 of 40 files with a bat recorded in it? So if X is, oh no, if Y is this binomial distribution, what's the probability that Y is greater than or equal to 32? And so I'm thinking Y is distributed as a binomial, sample size 40, probabilities of success 69%. And the central limit theorem tells me that this is approximately equal to the normal distribution with mean n times p and variance n times p times 1 minus p. Did I get that right? I don't think I got that right. No, I got that right. So what's my n times p? N is 40. P is 0.69. So n times p is 27.6. And n times p times 1 minus p is 8.556. So the central limit theorem says my probability is approximately equal to the normal distribution with mean 27.6 and 8.556. Remembering that this is the variance. So what is the probability that Y is bigger than or equal to 32? Well, it's 1 minus the probability that Y is less than or equal to 32. And I guess if we want to be technical, we should probably, if it's truly a complement, we should get rid of that. And this is important because this is what R calculates. And to put this in the language R understands, this is P norm 32 mu 27.6, and then standard deviation, which is the square root of 8.556. So if I throw that into R comes out with a number 0.663. So it looks like there's about a 6.5% chance that 32 of my files will have, or 32 or more of my files will have bats in them. And that kind of makes sense because this normal distribution, if it's got mean n times p and n times p is 27.6, that's the number of files I would expect. 32, I'm asking more. And I'm not quite asking a full variance more. And the standard deviation is probably less than 3. So it's more than 1 standard deviation away from this. So the further away I get from the mean, the less likely it's going to happen. So that doesn't surprise me too much. It seems a little low, but it doesn't surprise me. Okay, so this is the example that I wanted to show you. There is an issue. There is this issue right here of that. I think, and I didn't calculate this, I think the best thing to do is, since you can't have a fractional number of bats, it's to put in a 31 and do the calculation. That would be better for us. But I don't have that number right now. All right, and we've got, ooh, no, we're out of time. So I don't have much time to tell you about confidence, but let me just give you a 30-second, this is what I think we're doing. in statistics, we're interested in studying a population, and there's usually a number, a parameter that we're interested in getting about this population. And theta is a generic symbol that's used for these things. When we do statistics, we don't measure the whole population because it's probably outside of our ability to do so. Instead, we have a sample of members of a population. And from that sample, we get a sample statistic, an estimator. In this case, theta hat estimates theta. That will always or inevitably be different from the value of the parameter, the real value of the parameter. And our job is to understand what's the error, right? How different could that be? And so let's think of this as a theta axis. Our theta hat is going to be on there somewhere. The real theta is going to be somewhere else. And our job as statisticians is to take what we know about this population, okay? And it might be, what are the mean and variance of our parameter? Or what's the mean and variance, of our sample statistic? Or our sample mean and our sample variation of the sample statistic? I mean, there's all kinds of things that could happen. How do these numbers influence what we know about this error? And generally what we do in statistics is we say we have our estimator, and we're going to create an interval around that sample statistic. Sometimes it's centered on the parameter, but let's center it on our sample statistic. And that's an interval where we're pretty confident it contains the real value of the parameter. And the width of this interval is usually called our margin of error. And if you've been listening to news and reading about political polls, they talk about a margin of errors of political polls. So the next topic in chapter 5 is about building these confidence intervals, using information we know from our sample and about our population to figure out what the endpoints of these intervals should be. Our confidence is usually measured in a percentage. You know, are we 95% confident? Are we 68% confident? And the more confidence we want, usually the bigger the interval has to be. Okay? But that's what we're going to start talking about. And it's can be a confusing topic, so read it carefully. But that's what we'll start talking about next time, chapter 5. All right, thanks for sticking around for a couple more minutes. Sorry I went over. Stay well, stay healthy. See you on Thursday. No, campus is closed tomorrow, remember. Veterans Day.
Thank you, Dr. Miller.
Yep.
Bye, Professor.